Okay, welcome everyone. I hope you can hear me. So let's get started. Today we will continue the study of public key encryption. Last time we saw Al-Gamal encryption, and today we will see the RSA function. Note that RSA is typically known as an encryption scheme, but textbook RSA as such is not an encryption scheme directly. We will see why that is the case today. And we will see how to convert it into a secure encryption scheme. Okay, and then we will also pick some of the problems from the homework and we will see their solutions. So let me remind you the Ind security for encryption, right? It's called Ind CPA, the chosen plain text attack. It says the following. So you are given an encryption of, let's say, M0 and the public key such that PK, SK come from the key generation. And what we need is that this should be indistinguishable from the encryption under PK of another message M1 such that again PKSK comes from key generation, right? And this should hold for every pair of messages M0 and M1. And another very important fact to keep in mind is that any good public key encryption scheme must be randomized. And this is to avoid a very simple attack, because if it is deterministic, then an attacker can just encrypt the message on his own and just match it with the ciphertext. If it matches, then you recover the message. Okay, so now let's look at the RSA assumption. RSA was actually the first public key encryption scheme proposed by Rivest, Shamir, and Edelman in 1978, which is sort of 2 years after the seminal paper of Diffie and Hellman. But RSA is not the simplest public key encryption scheme. The simplest one, at least in my opinion, is Al-Gamal, which is sort of very straightforward and which is what we looked at in the last class. And then, of course, Rivest, Shamir, and Edelman, they got Turing Award for proposing RSA. RSA is used basically like everywhere on the internet right now. So before we look at RSA encryption, let's look at the RSA function. So it's helpful to view RSA as a function rather than as an encryption scheme directly. So we will look at the RSA function, which also leads to the RSA assumption. A lot of people say that RSA is secure, assuming factoring is secure. That is not true. The security of RSA requires factoring to be hard, but in fact, it requires more than that. The security of RSA is not equivalent to the factoring assumption. We will see that later on. Okay, so first step is, okay, maybe the first step is you pick two large primes P and Q. Such that P is not equal to Q. Okay, you can decide your length, which of course will be determined by the security parameter. You can pick primes of 512 bits, distinct primes, and that's your starting point. And then you compute what is known as the Rsa modulus. which is n, which is just p times q. Okay, so known as the Rsa modulus. Okay, and here keep in mind that Zn star is the group now. Zn star is the set of all numbers, all positive numbers starting from 1 up to n minus 1, which are relatively prime to n. Now the next step is to choose the exponent. Choose E to be from, oh, let me note the order of the group. So what is the order of Zn star? Order of Zn star is phi of n, where phi is Euler's phi function, right? Which is equal to p minus 1 times q minus 1, assuming p is not equal to q. And a very important thing to keep in mind is that given n, but let's say not p comma q, computing phi of n may be hard, right? Because phi of n requires knowledge of p and q. If I just give you n, it's not clear how you would do it. And in fact, that's one of the assumptions which RSA has. In fact, you can prove that computing phi of n is hard, assuming factoring the number n is hard. Now the next step for you is to choose an exponent. So you choose E to be, it's very important, something maybe strange here, to be from Z phi n star. Okay, and I'll try to explain why this is the way it is. Or in other words, is from 1 to phi of n minus 1 and relatively prime to phi of n. Not n, but phi of n. Okay, this is because E lives in the exponent. E is an exponent, right? So mod n becomes mod phi of n in the exponent, right? So that's why whenever we are talking about modular arithmetic in the exponent, you always want to talk mod phi of n. And why do we need it to be relatively prime? That we will see later on. Okay, so now let me define the RSA function. It's very simple. Rsa function is denoted by f n comma e. N comma e, modulus and the exponent, they are not the inputs to the Rsa function. They are actually hard coded inside the Rsa function. The input is some message x, where x is an element of Zn star. And the Rsa function simply outputs x to the power e mod n. Okay? Now, given x to the power e mod n, is there any way of recovering x? Right? So keep in mind, to recover X, you need to take the Eth root, right? If I have X squared, to recover X, I need to take the square root. If I have X to the power Y, sorry, X to the power E, I need to take the Eth root to recover X. So now the remaining task, sort of, which we have is there any way of taking the Eth root here? Okay, and turns out there is, and this is where this will play an important role. Okay, so given E, you can compute. So by the way, I'm just starting with an informal sort of understanding of RSA. We will have a more formal description of RSA just coming. So you have to compute a D such that E times D equals 1 mod phi of n. Okay. So first of all, why would this D exist? Any ideas? Does this D exist at all? And if so, how can we compute it?
So inverse exists for each element, right?
Okay, yeah, there are some answers on chat as well. Yeah, so basically it exists because if an element is relatively prime, so if E is relatively prime to this mod phi of n, then an inverse of E exists with respect to mod phi of n, and this is something which we saw earlier in the number theory class, right? And you can compute it using the extended Euclidean algorithm again. So good. Now we are almost done as far as recovering this X is concerned. Okay, so given D, I can now compute. So this is given to you mod n. I can raise this whole thing to the power D. What I get is X to the power ED mod n. Okay, and what is X to the power ED mod n? X to the power ED mod n is actually X to the power ED mod phi of n, mod n, right? And this follows from Euler's theorem. And what is this? This is just X mod n, because ED mod phi of n is actually 1. So you recover the exact same X which you started with. Okay, so the nice thing is, given D, you can invert and you can recover this function. You can recover the input X. Without D, it's somewhat less clear how to do that, right? And how do you compute D? So here is an important observation to keep in mind. You need the order of the group. You need phi of n to compute D from E, right? And on the other hand, computing phi of n actually requires the factorization of n. Okay, so unless you have factorization of n, it's not clear how you can ever compute this number D. And now we are already sort of making progress. It looks like E is almost like a public key, which would allow you to encrypt the message X, and D can be seen as like a private key, which would allow you to recover X, given the ciphertext X to the power E mod n. Okay, so this is good as far as intuition is concerned, but we have to stop right here. This is because Rsa function is unfortunately deterministic. This means that this cannot be a secure encryption scheme, right? So that's why RSA is not a secure encryption scheme. RSA is what is known as a trapdoor one-way permutation or trapdoor one-way function, which can be turned into an encryption scheme using some randomness, which we will see later on. So now let's see exactly what RSA is. Let's try to formalize what RSA is, and let's try to study this object and what we can do with it. Okay. So I specified the RSA function. Let me also specify the RSA assumption. Okay, RSA assumption basically says that given X to the power E mod n, you cannot compute X unless you have factors of n. Okay. So RSA assumption says the following: probability that for this should hold for every PPT adversary A. Probability that X to the power E equals Y mod n such that P and Q were large primes. N was computed at P as P times Q, and E was sampled from Z star of phi n. And in fact, normally E doesn't even need to be randomly sampled, even though that's what we are doing here. If you want your encryption to be faster, you want to choose E to be small, right? Because encryption requires a sort of exponentiation to E. The smaller E is, the faster you can do it. So typically in practice, E would be some number like 20, 25, and then D would be much larger. On the other hand, if you want inversion to be faster, then E and D must roughly be the same size. You cannot put D to be very small, because then obviously it becomes guessable, which is not what you want.
So E is not random, or is it random from a set of small numbers?
E can be fixed sometimes. There are some unsafe values of E, there are some safe values of E, and as you can expect, the safe and unsafe set, it kind of changes depending upon the advances in cryptanalysis and the attacks and so on.
Okay, thank you.
Typically, most values of E, fixed values, mostly it will be safe. Okay. Now what you do is you sample a random Y from Zn star, and then you try to invert. You try to invert with respect to this Y. So you give the adversary A, you give the adversary E, N, and Y, and adversary outputs some X. Okay. And now we are looking at the probability that X to the power E is indeed Y, which means that adversary successfully inverted this. And what we want, this should be negligible in N, rather size of N. Okay, so essentially Rsa assumption says that given the Rsa modulus, given the exponent, inverting the Rsa function is hard. So this essentially suggests that Rsa gives you a one-way function. Okay, not very interesting. We already constructed one-way functions before, just from factoring in a much simpler way. But now the interesting observation is that Rsa function is also a permutation. And this is the interesting part, right? Because we have not constructed one-way permutations so far. So why is Rsa function a permutation? Any thoughts?
So because that element can be a generator, right? And when you exponentiate it, like it will give you each time a different member of the group.
I mean, maybe that proves one-to-one, not necessarily a permutation.
Like you can do it for all elements in the group, and like it is one-to-one, and it is one way. Then it is one-way permutation, right?
So one-to-one and one-way does not imply that it's a permutation. So what you need for a permutation is that the domain and the range should be the same. Input and the output should belong to the same set, which is actually the case in Rsa, right? So in Rsa, x comes from Zn star, and f of x, which is x to the power e mod n, also in Zn star. Okay, so that's the first observation. The first observation is that the domain and the range are exactly the same. Second observation is that there's a one-to-one mapping between elements of the domain, which is your input, and elements of the range, which is your output. And this follows from the fact that given output, there exists a unique input, right? And we have already seen how to compute this unique input. If you have D, then given the output, you can just recover this input, right? No multiple possibilities or something like that. There's just one input. Given the output, I can recover it if I have D, which means that there exists a unique input given every output. Okay, any questions so far? So Rsa is one way, Rsa is a permutation. What else? The interesting thing is Rsa also comes with a trapdoor, which is D, which allows you to invert this, this function. So that's a property which we have not thought about before. Certainly a one-way permutation doesn't require this property. So Rsa does give us something extra even compared to a one-way permutation. So Rsa is what we call a trapdoor one-way permutation. And let's try to define what trapdoor one-way permutation is. So let me try to define a trapdoor one-way function. So trapdoor one-way function is a collection of functions. It's not a single function because the exponent e and the modulus n, it's sort of hard coded in the function. Different values of e and n will lead to different choice of the function. So let's denote this collection by capital F, which is sort of Fi, where it goes from some domain to some range. Okay. And I is in some set capital I. So we say that this is a family of trapdoor one-way functions if the following conditions are satisfied. First condition being, first of all, there's a function sampler. You should be able to pick from this set. This just corresponds to picking P and Q and picking the Rsa modulus and the exponent. So function sampler requires that there exists a PPT algorithm gen which outputs some I, Fi, and a trapdoor T, where Fi is part of this family F. Okay. So when you sample the function, you get the description of the function and you get a trapdoor, the trapdoor being D for RSA. Second property is the input sampler. Which just says that you can sample randomly from the domain. The third property says that the function can be efficiently computed. So Fi of x runs in polynomial time for all I and all x. Now, what is the fourth property? Fourth property is that this function should be hard to invert without the trapdoor. Just says the following for every PPT adversary A, right? The probability that A is given the description of the function Fi and A is given some Y, which is the output. A has to produce some X prime such that F of X prime equals Y. So this is the probability that A is able to successfully invert Y, where I, Fi, and T are generated properly. X was sampled from the domain. Y was sampled from the range. Is actually, wait, I think we don't need this if it's a permutation. because x and x prime will always be the same. So this probability should be just negligible. Okay. Finally, what we want is that if you have the trapdoor, then actually you can invert this in polynomial time. Easy to invert with trapdoor. Okay, so we will just simply say that there exists a polynomial time algorithm which is given I, Fi, the trapdoor, and also Y, and it outputs X such that f of X equals Y. Okay, if you have the trapdoor, you can invert in polynomial time. The last property just says that for all I, Fi is a permutation. So I am defining trapdoor one-way permutations directly. You can also define trapdoor one-way functions by just leaving out this last property, but then you have to deal with x and x prime not being equal. This is a much cleaner definition. Okay, any questions? And what we will show is that based on the RSA assumption, RSA is actually a trapdoor one-way permutation. Okay, so now let's see. So trapdoor one-way permutations based on the RSA assumption. Okay, and this in some sense we have already seen. First, we need to specify the function sampler. So one is function sampler. And how does it work? You choose P and Q to be large primes. Then you compute N to be P times Q. Then you sample E from Zn star. And then finally, you compute D such that Ed equals 1 mod phi of n. Okay, so now what is your function and what is your trapdoor? So your I and Fi, which is essentially the description of the function. This is basically E and N, which would be public, and your trapdoor is just D. Okay, makes sense. Second is your input sampler. Input sampler is just you can sample uniformly from Zn star. Okay. Now, if you don't know factorization of n, can you still sample from Zn star? Can you still test if if something is in Zn star or not. Yeah, this can be done. So what you do is you can pick a random number from 1 to n, and then you just compute the GCD. Test if GCD of x and n is 1. And by the way, to compute the GCD, you don't need factors of n. Just the Euclidean algorithm tells you how to compute a GCD. It's one of the oldest algorithms, I think several thousand years old. Third is, of course, the Rsa function can be computed in polynomial time, just a modular exponentiation. If you have taken 251, then we actually see a very efficient algorithm for modular exponentiation, which is based on the square and multiply. Fourth property is hard to invert. And this, by the way, follows from the Rsa assumption. Let me show it to you. Let's keep the board here. So Rsa assumption says that adversary is given the Rsa function, which is just e comma n, and adversary is given some random y from Zn star. The probability that adversary can output an x such that x to the power e is y mod n, this should be negligible. Is e supposed to be generated from? Yes, good point. I missed. This is phi of n. Thank you. Okay, so hard to invert follows from the Rsa assumption. So number 5 is easy to compute, easy to invert. With Trapdoor, and this is true, you can just use d, and given x to the power e, you can compute x. This is something which we have already seen. And the last point is fi is a permutation. So again, something we have seen already. Domain and the range are the same regardless of what n is or e is. So for every value of I, fi is actually a permutation. Okay, so good. So Rsa is a trapdoor one-way permutation. Any questions? Now, why do we bother with a trapdoor one-way permutation? Can you do something with trapdoor one-way permutation, something that we actually need, like encryption scheme? So we will see how to convert a trapdoor one-way permutation to an encryption scheme, to a public key encryption scheme, which will be secure according to our good IND CPA definitions. And let me keep the definition of trapdoor one-way permutation. So I'll give you a general compiler which can convert any trapdoor permutation to a secure public key encryption scheme. You can use it on RSA, you can use it on anything else of your choice. And this uses old ideas which we have already seen before. So we used one-to-one functions, or let's say one-way permutations, to construct a secure symmetric key encryption scheme. And this used hardcore predicates, which is also what we will do here. So public key encryption. Using trapdoor one-way permutations. Okay, and we have to specify 3 algorithms for public key encryption. We'll look at the homework problems later on. So the 3 algorithms are key generation, right? Encryption and decryption. Okay, so how does key generation work? As you can expect, the key generation just consists of running the function sampler. So run the function sampler. Okay, and the function sampler gives you I, Fi, and the trapdoor tau. Okay, and as you can expect, your public key is just I and Fi, which is the description of the function. Your secret key would just be the trapdoor. Now let's say you want to encrypt some message under the public key. Okay, and by the way, it's important that message must be part of the domain. In particular, for RSA, message must be part of Z and star. So how do you encrypt? And here we can already think about something which we must do. We must use some randomness for the encryption to be secure. Okay, so let's just close our eyes. Let's just generate some random numbers first. So actually, we will try to encrypt a single bit message. Sorry. Okay, so first step is you sample R from the domain. Okay, and this can be done using the input sampler here. Now your ciphertext consists of Fi applied on R. Okay, now given Fi, if you don't have the trapdoor, you don't have R. Okay, R is one way for you. How can we use this to encrypt the message? Any ideas? So how do we encrypt a message using something which cannot be computed? Right? I mean, one option normally is I can just publish R XOR M. This is option 1, R XOR M. But this doesn't quite work because R is one way, right? The guarantees that the adversary cannot compute R entirely. Maybe adversary can compute some bits of R, right? One-way functions can leak some part of their input. So this is not good. What you want is you want to use the hardcore predicate of R here. And that's why M is just one bit. So you can publish M XOR the hardcore predicate of R. And let me call these two components of the ciphertext where HI is hardcore predicate of FI. Okay, every one-way function has a hardcore predicate, something which we have already seen. Now, how do you decrypt? You are given the secret key, which is the trapdoor. You are given the ciphertext. Okay. So decryption has two steps. Use the secret key to recover R from FI of R. FI of R is just C1, which is part of the ciphertext. And then compute HI of R and recover M from C2. Right? So this is why trapdoor is useful.
So, but hardcore predicate is just a single bit, right? Like, how will we take an XOR with the entire message?
So yeah, that's why message is also just a single bit right now. How do you encrypt a longer message? Just encrypt bit by bit. So for every bit, you will choose a different R and compute the hardcore predicate and just XOR the relevant bit.
Okay, thank you, sir.
Okay, good. So now, how do we prove security, right? The security proof basically follows from the fact that this FI is a one-way function in the absence of the trapdoor. So by the way, correctness should be obvious here. And in the security proof, what we want is we want to show the following. So we have the public key, which is you are given. So first you are given the ciphertext FI of R, M0 XOR HI of R. And then you have the public key, which is I comma FI. Right? This is your hybrid 0. And then you will have the first hybrid, where you would replace this hardcore predicate with a uniform bit B. Everything else remains the same, such that B is sampled at random from 0, 1. How do we prove H0 and H1 are indistinguishable? Just by relying on the fact that if FI of R is a one-way function, it implies that hi is a hardcore predicate, which implies that its output must look uniform. And then we can do the usual steps. We have done that so many times now. You can change this to M1. This is now exactly like a one-time pad. Okay, and then finally we will have H3 where we will change B to just HI of R. And then H3 is exactly your ciphertext which encrypts the message M1. Okay. And again, as I said before, how do you encrypt a long message? Just encrypt it bit by bit. So the scheme is not used in practice, by the way. This is probably the simplest way to convert RSA to a secure public key encryption system. But there are schemes which are sort of much more practical. The reason this is not practical is because you need to chop off the messages, you need to encrypt them bit by bit.
And like for each bit that we transfer, we are actually transferring a much bigger number also with it, right? Like the thing that will get inverted.
Yeah. For example, Fi of R is a group element of Zn star. So that's definitely not a single bit. So each bit of the message gets expanded to a much bigger string in the ciphertext. So now we are done with public key encryption. Next time we will start message authentication codes and digital signatures, I believe. And in the remaining time that I have today, I want to pick some of the problems from the homework. And hopefully you will have the graded homework back in a couple of days. We are targeting Friday. Okay, I don't know if you can read it. So I got some feedback from the TAs regarding which questions were sort of tricky and people made mistakes. So let me start with the last question, which is question number 9. So problem 9. And I'm sure that you cannot read it. So let me just explain the problem to you. So you are given two different PRGs. You are given G1, which expands n bits to 2n bits, and you are given another PRG which expands the same n bits to 2n bits. And now you define another function. Let's call it G, which will expand n bits now to 4n bits. Right? And G simply takes the n bit seed as input. And G is defined to be G1 of S concatenation G2 of S. Okay. Now the question was, is G also a PRG? Does this give you sort of a uniform looking string of 4n bits, assuming that G1 and G2 are PRGs, right? So the answer to this question is no, right? And here's a very simple counterexample. What if G1 equals G2? Okay, if G1 equals G2, then G1 is still a PRG, G2 is still a PRG, and yet, regardless of how you pick the seed, the first half of the output and the second half of the output would always be identical, which is very unlikely to happen in a uniform 4n bit string, right? So it's very easy to distinguish this type of string from a uniform string. So this is not a PRG at all, but that's not the end of the answer, right? So you can give a counterexample, but you are also expected to show where the hybrid argument breaks down. Okay, so this is a good counterexample we can keep in mind, but let's even forget about this counterexample. Okay, let's try to do our usual proof. So let's try to start with the distribution G1s concatenation G2s. By the way, feel free to stop me anytime if something is unclear or if you have any questions. And here the seed is sampled uniformly. So this is our first distribution. What we can try to do now is, we are used to replacing things one by one, right? So what we can try to do is, let's try to replace the output of G1 by uniform. So let's try to put the uniform, let me call it, say Y1 concatenation G2 of S, where S is uniform, and Y1 comes from U2n, the uniform string of 2n bits. Right, and presumably after that point you would replace G2 of S by another uniform string, and then you will end up with a completely uniform output, right? So this is sort of the hybrid argument which you would naturally consider. Now you might be tempted to write that H0 is computationally indistinguishable from H1. Maybe you don't realize this, there's this counterexample, that's fine, right? When you're writing a proof, you don't need to exhaustively think about every possible counterexample. That's the point of a proof. If it goes through, it goes through, right? So why doesn't it go through? So let's try to prove it. And here I'm giving sort of a natural argument which you can try to write. So let's try to prove it by contradictions, say not. So you are given a PPT adversary A, and which can distinguish H0 from H1, right? We can try to build another PPT adversary. Let's call this B. Okay, now B will take Y1 as input. And Y1 is either G1 of S such that S is uniform, or Y1 could be a 2n-bit uniform string. And the goal of B would be to distinguish the case where Y1 was coming from here versus here. If you are able to do that, you contradict the fact that G1 is PRG. Okay, so good. Now what B1 does, what B does is B takes as input Y1 and works as follows. Step 1 is invoke the given PPD adversary A on Y1 concatenation G2 of S. If A can now distinguish, and I'll ask you what is wrong with this hybrid argument. A can now distinguish H0 and H1, then B can actually distinguish this case from this case. G1 of S, S is uniform from U of 2n. So B can distinguish the case where Y1 was sampled from this versus this. Okay, and if A has a noticeable advantage, then B also has a noticeable advantage. Okay, so this almost looks like a standard hybrid argument. What is wrong with it?
You can't compute G2 of S.
Good. Yeah. The main problem here is B does not have G2 of S. Right? B is given G1 of S, or maybe B is given uniform, right? But B doesn't have the seed, right? What we can try to do is, what if B samples S at random? And then B invokes A. What is wrong with this?
G1S and G2S won't be same.
Yeah. So if B samples S at random, then basically this S and this S, they are independent, right? They're different. Then you end up with, then you have basically either G1 of S1 concatenation G2 of S2, or if Y was coming from here, you have U2N concatenation G2 of S2, right? But you never have this. So that's why the hybrid argument breaks down entirely. And one very nice technique to see if a proof breaks down or not right away without going through all of this is always remember that the security of the PRG relies on the seed being uniform, right? In the definition, you always choose your seed to be uniform. But now, if I want to rely on security of G1S, given G2S, is the seed uniform? I don't know, right? Maybe not. So security of one-way function relies on input being uniform. Security of PRG and PRF rely on the seed being uniform. Security of encryption relies on the key being uniform and the randomness used as part of encryption being uniform. It doesn't rely on message being uniform, and so on, right? So for every cryptographic primitive, you should keep in mind what is uniform and what is not. Any questions?
So can you re-explain this part where you just told about like what is the best way to figure out that the proof is wrong? I could not understand that part properly.
Mm-hmm. Okay, so let's look at this step. We were trying to argue that G1S is indistinguishable from uniform given G2S, right? But the security of a PRG requires that the seed must be uniform. Now the question is, given G2 of S, is S uniform to the adversary A? If the answer is yes, you can make this jump. If the answer is no, or I don't know, I cannot prove it, you cannot make this jump. And given G2 of S, at least I don't know how to prove S is uniform, right? Maybe the output of the PRG leaks like half of the seed and only uses the other half in a non-trivial way. Well, okay, maybe not. But in any case, it's not clear. Okay, so this is a very important point, and this is really like the core of hybrid arguments. I have tried to explain that before in the class. I mean, really, like if you understand what the security relies on for different primitives like encryption, PRF, PRG, you will do most of the hybrid arguments correctly. You will be able to sort of avoid the common mistakes. So that's why I think this question is so important. Anything else? So now let's try to get through a couple of other questions. Okay, so which one should we pick next? I think maybe 6 is a good idea. So what is the problem 6? Actually, maybe we should do 5 and 6 together. Let me do 5 first. I think 9, 5, and 6 were sort of the questions where students did not do as well as expected. So in question 5, you are given you are given a one-way function, which is you are given a one-way permutation. Okay. Okay, then should we do 4 before 5? Should we do 4 before 5? Or should we directly do 5? Okay, let's do 5 directly. So you are given a one-way permutation G, right? So G goes from n bits to n bits. And now your goal is to prove that G, which is the composition of G, composed with itself, is also a one-way permutation. So there are two parts to this question. First, you need to prove that this is one way. Next, you need to prove that this is also a permutation, right? So what is G composed with itself? This is just G of X. Now we know the following. Probability that A is given G of X and A outputs X such that X is picked uniformly from 0, 1. We know that this probability is negligible in size of n, right? This is just the definition of a one-way permutation. My claim is that this also implies that probability that A of G of X equals X, given that X is now picked in a somewhat strange way. X is actually G of X prime, where X prime is picked uniformly. My claim is that this is also negligible. And why? Because you have to look at this distribution and this distribution. My claim is that these distributions are identical. Okay? And the fact is, output of any one-way permutation on a uniform input is also uniform. Right, and this is something which we have seen when we were trying to prove that we were trying to prove the PRF. We are trying to construct PRFs from one-way permutations. Or it was PRG. So our construction of PRG was something like this: f of s and h of s, right? Here s was uniform. We tried to argue that f of s is uniform. And given f of s, h of s is also uniform. And intuitively this follows, because as long as domain and the range are the same, if your input is uniform, then your output is also uniform. So you can look at the that lecture. So this already proves that. And by the way, what is this distribution? This is the same as saying that probability of A of G of G of X prime okay, do we have the right number of brackets? So this is the same as saying the following, where X prime is chosen These are really the same statements, right? I am just putting the value of x as g prime of x. Okay, and by the way, this also implies that probability that A can output g of x prime, probability that A outputs x prime is also negligible now. And why is this the case? Any guesses?
G composition, G is a permutation.
Doesn't require you to.
So basically, since like that x prime will always be equal to like it is one way, right? So once like g of x equal to g prime of x, then x has to be equal to x prime.
Yeah, but you are given the fact that A cannot compute g of x prime, right? Maybe A can compute x prime. How did we conclude that A cannot even compute x prime? So this follows from the fact that g is a polynomial time function, right? Because if, let's say, A can compute x prime, then A can also compute g of x prime. Just because given x prime, I apply a polynomial time function and I get g of x prime. So if computing g of x prime is hard, computing x prime also must be hard. Right, so this proves that this is one way. Okay, does this make sense? Any questions? And now let me skip proving that. You also need to prove that the composition is a permutation. But I think students generally did well on this part, if you realize that you have to prove it. So let me try to cover question 6 as well. So question 6 asks you to prove the following. You are given a one-to-one function. It's not necessarily a one-way function. Let's call this function f, which has a hardcore predicate. Your goal is to prove that f is also a one-way function. A strong one-way function. Okay. Actually, this is very simple. So suppose not. Say you are given a PPT adversary A, which inverts f with noticeable probability. Okay, and now the idea is that if you are able to invert f, then you can compute the hardcore predicate absolutely with probability 1. But if you are unable to invert f, then you just output a random guess for the hardcore predicate, right? And because you are inverting with noticeable probability, with noticeable probability, your answer is always correct. Remaining times, your answer is correct with probability half. So overall, your probability of guessing correctly is actually slightly better than half. Okay, so your adversary B, which takes Y as input, it works as follows. Step 1, you run A of Y, and if A gives X such that Y equals F of X, then great, I can compute the hardcore predicate, which is H of X. Else output a random bit. Okay, so here you are successful exactly with probability half. Here you are successful with probability 1. When you try to compute the overall probability of success, it will be some half plus noticeable, assuming that this case happens with noticeable probability. So we will stop here, and I am around for questions.
Thank you, Professor.